Hello everyone, this is Gaurav Mishra and you are watching GM Physics. And I welcome you all. All right, so in this video lecture, we are going to study scalars and vectors in detail. First of all, we'll look at understanding scalars and vectors through an example. We'll take a very simple example, a real life example, to understand what exactly are vectors and how they are different from scalars, or how physical quantities can be broadly classified into two categories. One is scalar, another one is vector. Then we'll have examples of scalars and vectors. We'll take another example, look at some physical quantities related to that given example, and we'll classify under scalars and vector based on what we saw in the previous discussion, that is understanding scalars and vectors through an example. Then we'll see, do vectors follow algebraic addition? Means we'll make an attempt to add two vectors in the same way like we add any general quantity using rules of algebra. So we have to see whether they follow algebraic addition or they don't follow. We will make our attempt to add them in the same way. If they don't follow, we'll just check it whether they follow or not. After looking all these things, then we will define or we'll develop a proper definition of vectors. All right, so let's try to understand what exactly are scalars and vectors through this very simple example, a real life example. What you are seeing, this green region, this is a top view of the classroom, right? And these black ones, A, B, C, D, E, these are students sitting in the classroom. You are looking from the top of the, you are looking from a hole in the roof of the classroom. So this is what you'll see. These black ones, students, and I have named them as A, B, C, D. I have not given them usual names like Ram, Sham, Gaurav, etc. This is the teacher standing, and this is the board who is teaching, right? So just listen to a conversation between the teacher and the student. And from the question and answer, means teacher will ask some questions and the student will answer. So through this question and answer, try to understand what exactly are scalars and vectors. So after analyzing those two questions from the teacher, we will compare other physical quantities with those two questions only. And I hope you'll understand what are scalars and vectors. So look at this. Teacher says to C, teacher asks C, yes, C, get up. So C gets up. So, yes, sir. What is the total number of students in the classroom, including you? So he starts counting the heads in the classroom. A, B, C, 1, 2, 3, 4, 5, 6, 7, and 3 rows, 1, 2, 3. So 7 threes are 21. So he says, sir, it's 21 in the classroom, including me. Okay. So the first question was total number of students in the classroom. So the first question is total number of students in the classroom. So what is that? He counted the heads of the students and he got the answer 21. So the answer to the first question is 21, a numerical value, right? Just 21. And I think this is the complete answer to this question. It doesn't need to specify the position of individual students, like A is sitting here, J is sitting here, U is sitting at the last of the class. No, this is not at all required. The teacher has asked simple question, what is the total number of students in the classroom, including you? So C has answered 21. Now listen to the second question the teacher asked to C. Yes, C. Where is D? Assume that teacher doesn't know the names of the students except C. He knows C because C is the class monitor. So he knows his name. He doesn't know about other students. But he knows a student named D is there in the classroom. So he's asking, he wants to locate him exactly. Where is he sitting? So he says, yes, C, where is D? So let's say C knows about all the students. So D is sitting at a distance of 10 meters from him, right? J is also sitting at a distance of 10 meters from him. B is also sitting at a distance of 10 meters. These all students are sitting at a distance of 10 meters. Assume, right? So C says, yes, sir, D is sitting 10 meters away from me. So teacher tries to figure out who is D. This student is also sitting at a distance of 10 meters. This is also sitting at a distance of 10 meters. This is also sitting at a distance of 10 meters. Where is D? I can see 3 students are sitting at a distance of 10 meters from you. So she said, sir, to my left, to my left. So why didn't you say at the beginning? I had to count all the students. There are so many students sitting at a distance of 10 meters from you. So what was wrong in his answer? Initially he said 21, just a numerical value. And teacher came to know that yes, 21 students are present in the classroom. But when he says 10 meters from him, teacher is not able to locate who is D. What is wrong in this? The only thing which he didn't provide is the direction. He said 10 meters, that is correct. But 10 meters in what direction? 10 meters in what direction with respect to C? So to left. So this is not only 10 meters. Along with 10 meters, we have to provide one more information, that is direction. Like for, in this case, you see to left of C. So let's write this second question. When teacher says, where is D? So he wants to know the position of D with respect to C. Means if we look at this question conceptually, he's trying to find the position of D. He wants to locate D exactly in the classroom, right? Because he doesn't know the names of the students. Are you getting the point? So he wants to know the position of D with respect to C. Indirectly, you can say, or alternatively, he wants to know position of D with respect to C. So let's write the second question. So the second question is position of D with respect to C. And the answer to this question from C was 10 meters, which was not correct. It was wrong. When he says 10 meters to my left, means to the left of C, to the left of C, then it becomes a complete answer, exact answer, right? Correct answer. So here you see there is a magnitude in this quantity and there is a direction in the quantity. Let's write it. This is the magnitude of this quantity, which is position of D with respect to C, and this is direction of that quantity, that is position of D with respect to C. So there are physical quantities which cannot be completely expressed just by writing magnitude or numerical value. It's not only position of D with respect to C. There are so many other quantities which cannot be fully expressed just by writing or mentioning a numerical value, a magnitude. Along with the magnitude, you'll have to specify a direction with respect to some reference. Like, for example, here the reference was C. With respect to C, D is sitting to the left, right? So such physical quantities which have magnitude as well as direction, or which cannot be expressed completely just by writing magnitude, are called as vectors. And those quantities which can be completely expressed just by writing a magnitude are called as scalars. So all the physical quantities that exist in the world, they can be broadly classified under these two categories. One which can be completely expressed just by writing the magnitude, and the other which needs magnitude as well as direction. So that group of physical quantities are called as scalars, which just needs magnitude, and this group of physical quantities which have both magnitude and direction can be grouped under vectors. So in short, we can write vectors means magnitude plus direction. Are you getting the point? Vectors means magnitude plus direction. All right. So now we are going to classify some physical quantities, real life physical quantities related to this car under the heading scalars and vectors based on what we have learned so far. That is based on magnitude and direction. Whether a given physical quantity has only magnitude or it has both magnitude and direction. So let's look at some of those physical quantities. So the first one is mass of the car. What is mass? Mass in fact talks about the total matter contained in the body, not how much matter is present where. It doesn't talk about its distribution, right, with respect to a particular reference. It talks about same like total number of students in the class. It's total amount of matter contained. So mass of the car in that sense becomes a scalar quantity. So mass of the car is a scalar. So I'll write S for it. Now it is volume of air inside the car. So volume of air means the total space available inside the car for the air particles, or the total space occupied by the air particles inside the car. Means the space which is available for passengers and drivers. It doesn't talk about anything else. So the volume of the air, that is total space available, is again only a magnitude, just a numerical value. So again, it becomes a scalar quantity, right? Now, temperature of the engine. So though we'll study about temperature in detail in thermal physics, for right now, understand temperature as the vibrational kinetic energy of the particles. So it doesn't talk about the motion, the direction in which the particle is vibrating, what is its speed, what is its direction of motion. No, it talks about the average kinetic energy associated with that motion of the particle. So again, temperature is a scalar quantity because it is not concerned about direction, right? When you talk about temperature, you talk about conceptually the average kinetic energy associated with the vibration of the particles of that given body. So again, it becomes a scalar quantity because you are not talking about direction, or direction is not required. For example, when you measure the temperature of the body, you say 98.6 Fahrenheit or temperature of water 25 degrees Celsius. You don't specify the direction, right? So this is a scalar quantity again. Now let's talk about speed of the car. What is the speed? Speed is in fact the rate at which the length is being covered by this car, right? So suppose that the car is moving at a speed of 60 km per hour. It simply means at present, the car is moving in such a way that in 1 hour, it will cover a length of 60 km. In what direction or how it will move and then cover, these things are not contained in speed. The speed only talks about the rate at which it is covering the road or covering the length of the road, right? So again, since we are not concerned about direction here, we are only concerned about the magnitude, the length per unit time, per second, per minute, per hour. It again becomes a scalar quantity. Now let's look about velocity of that. Now it becomes a different quantity because when you talk about velocity, you talk about two things. One is the rate at which the car is covering the length right now, and the direction in which it is headed towards at present. So let's take the conventional direction. This is east, this is west, this is north, this is south. So at present, the car is moving at a speed of 60 km per hour. And the direction of motion at present is towards east. So these together make velocity. Means when you talk about velocity, you will say for the car 60 km per hour along east. When you say only 60 km per hour, then it becomes a speed. When you say 60 km per hour along east, then it becomes velocity. So velocity, since it specifies the direction as well, it becomes a vector quantity. So here we'll write vector, right? Forces on the car. Again, we'll study about forces in detail in the chapter The Forces or the Newton's Laws of Motion. For right now, you should understand that force is also vector quantity because it has a specific direction. For example, When you talk about gravitational pull on this car, let's assume it's 600 kilogram car, then the gravitational pull is only in vertically downward direction of 6,000 newtons, right? So it is vertically downward in no other direction, no other direction. It has a specific direction. So when you say forces, you say this much along this direction. You just don't say 10 newtons or 20 newtons or 6,000 newtons. So gravitational force, then you will say 6,000 newton vertically downwards, right? It has a specific direction. So again, it becomes a vector quantity, right? Now let's look at the last quantity for this example. Displacement of the car after 1 minute. So assume the car is present here at t is equal to 0. And after 1 minute, the car is found to be present at this point. Let's say the car is present here, which is 100 meters away from the initial position. So car has been displaced by 100 meters in 1 minute. Along which direction? Along east. So when you talk about displacement, you just don't talk about how much, by what length it has been displaced. You also talk about in what direction. So its initial position, that is t is equal to 0, is this, and final position, the straight line distance between them is 100 meters, and it is towards east. So our displacement will be something like this, 100 meter towards east, right? So again, it's a vector quantity because you are talking about both magnitude and direction. So it becomes a vector. So for your understanding, I have finally classified the given physical quantities related to the car under scalars and vectors. So mass, volume, temperature, speed, and many more such quantities which have only magnitude are called scalars. And velocity, force, displacement, and many other physical quantities similar to it, which have both magnitude and direction, are called vectors. So I hope now you are understanding the difference between these two physical quantities and how to classify them under vectors and scalars. All right, so let's see if we can add two vectors algebraically. And since we are talking about vectors, I'm taking a reference for direction. This is east, this is west, this is north, this is south. The usual convention, right? Now assume a person starts from this point and moves along east for 10 minutes, right? So this is his first displacement along east direction. How much? 10 meters. So let's call this D1 vector. D1 vector. We have not studied how to represent vectors, so I'm not using proper representation of vectors right now. I'm simply trying to make you understand whether two vectors can be added algebraically or not. So let's call it D1 vector, and that is equal to 10 meters. Okay. So this is my first displacement. Now again, person moves for 10 meters along east direction. So this is his second displacement, D2. This is along east, and how much? 10 meters. Try to connect with the previous example. We defined roughly what is displacement from initial to final position, right? That is a displacement. It shows the direction in which the body has displaced. So the body displaced, the person displaced for 10 meters along east direction, that is his first displacement. And again, after some time, he start moving and displaced 10 meters along east direction. So he has two displacements, D1 and D2. What is his net displacement? So starting point is this, ending point is this. How much is this? It is 20 meters, 20 meters, right? Along east direction. And this is my D net, net displacement. So if I want to find D net, it is composed of two displacements, D1 and D2. So I am closing my eyes and simply adding, following the rules of algebra. I did D1 plus D2. So D1 is 10 meters. Forget about direction now. I'm simply using law of algebra. And first of all, let's check if we get the same magnitude by adding algebraically. So 10 plus 10, how much you are getting? 20. And how much is the net displacement? What is the magnitude of the net displacement? 20 meters. So by adding, you are getting 20 meters. So from here, we can assume that vectors follow algebraic addition. But let's look at the second example. Suppose again the same person moves along east direction by 10 meters, right? And he stops here. So this is his first displacement. Let's call it D1 vector, right? So after some time, now he moves along north direction by same length, that is 10 meters. So this is 10 meters along north direction. This is my second displacement, D2 vector. It is not along east like the previous one. So now if we find the net displacement, so this is his starting point and this is his ending point. For this much part, we are interested to calculate net displacement. So now his net displacement is this much, right? So this is the net displacement from starting point to ending point. So we need to measure this length to find the magnitude of the net displacement. So let's find out. First of all, I'm going to use algebraic addition the same way as we did. So since the net displacement is composed of D1 and D2, so I'll add them algebraically. So D net will be D1 plus D2, 10 plus 10, 20 meters, right? So according to algebraic addition, my net displacement should be 20 meters. Now let's see exactly how much is this. Means I want to find the value. Does it have exactly 20 meters, the way we got using algebraic addition? So let's see. This D1 is along east and this D2 is along north. So the angle between these two lines is 90 degrees. And my net displacement is, this is a starting point, this is the ending point. So in fact, it becomes the hypotenuse of this right angle triangle, whose base and perpendiculars are of length 10 meters, 10 meters, right? So using Pythagoras theorem, we can find base square plus perpendicular square root of that. So 10 square plus 10 square. How much is that? 100 plus 100, 200 root of that. Means you are getting 10 into root 2. Root 2 is 1.414. So you are getting approximately 14.14 meters. This is the real value of the net displacement, which is not 20 meters. It means at one place we see algebraic addition is followed, at other place algebraic addition is not followed. So which is the special case? In fact, this is the special case. Only here, coincidentally, algebraic addition is giving the exact value. Whether you check for displacement like this, displacement like this, displacement like this, nowhere you are going to get the same result as obtained using algebraic addition. So we say vectors don't follow algebraic addition. Now what they follow, that we'll study in detail in the coming lectures. But for right now, we understand that vectors don't follow algebraic addition. They follow some other special laws of addition, which we call vector law of addition. So now we can define vectors. We can say vectors are those physical quantities which have both magnitude and direction and follows vector law of addition or don't follow algebraic addition. So let's write the definition of vectors. All right. So vectors are those physical quantities which have both magnitude and direction, important, and follow the vector law of addition, very important, follow the vector law of addition. Examples are, as we saw before, displacement, velocity, force, etc. So I hope you have understood what are scalars and vectors in detail, how they are different, and do vectors follow algebraic addition, and finally the definition of vectors. So keep practicing, keep learning, and keep growing. Till then, bye bye, all the best.